Okay, let's look at the pyro market. Is a technology. It's again, once you discover something, it's been improved since 1996 in a number of different ways and used for different applications, including the next generation sequencing. So here is, in fact, most of these presentations are from the company itself, what they provided us, how you use it, and what they provided to us. You have a flexible assay design, number one. You have these PCR primers. Usually you use a biotinylated primer on one side and a regular one. You can amplify that. So that's in preparation to your gene and getting it to the sequencing level. And then if your region of interest is in a defined area, we had some discussion last week with some of you, I think outside. Okay, what if my region of interest is here? Do I design a primer here or here, right? That type of discussion we had on Friday. So you get as close as possible if you are doing sequencing. If you are amplifying it first, it's good to have a broader. Sequencing it, you get closer. The reason is, especially pyrosequencing, it's got short reads, right? Not very long ones. So we develop a sequencing primer. There are some criteria, but similar type of criteria, shorter than a regular primer and so on and so forth. But let's assume this is your region of interest. Okay. But you have lots of flexibility in terms of designing it. Okay. So one of the things they recommend is an easy primer designed standard biotinylation of one of the primers that enables you later on to detect it successfully. Okay. And by the way, one of the things I really liked when Biotage came out with pyrosequencing is their software. Really helps you design. You give it a gene of interest. It really designs very nice primers, nice sequencing primer as well as amplification primer, and recommendation for biotinylation. So they have a very friendly software. It's a tag, just like you attach fluorescent label or other various labels. So it is biotinylated one. The software is just quickly shown here. It's all-in-one software. It designs a complete genetic assay for you. It's easy to use, no prior design required. Yeah, it's got some marketing here, but it's very nice software. You import your gene directly. You can access it from the National Center for Biomedical Information database, and then you import it. Or you can decide, I want to use this primer and this primer. You enter it in this window and ask the software, is this a good primer? It will tell you. Or it will design for you and gives you many choices. And primary choice, I'll give you this, and that's how, in fact, we used the software tremendously to develop a pyro-based MLST, even if we didn't like the outcomes very much. And then once you do that, you select the primer, you order it, just the regular way of ordering primers. By the way, let me ask you this, since I don't know the answer so far. I may not have asked, but those of you who use a PCR or cloning, where do you order your primers? Where do you get the primers from? Ethiopia? Kenya? South Africa? Where do you get it? It's not a scientific question, but yeah, where do you get it? From Germany, from a collaborator. So if you wanted to have the primers here in Ethiopia, can you get it? Can you order a primer? Oh, you didn't search, but there might be some sources. Do you know, anybody knows the answer?
It's possible as far as you think, because they have technology. So and then you can use this. There is online coding system. There is a possibility.
Okay, well, there's a possibility to get it, but I'm just, yeah, it wasn't a scientific question, but more technical. But you get it from abroad, or you get it from here. Yeah, online you pay everything. Then they send it from Germany. Okay, yeah, okay. I'm just curious, but that's not so much scientific question. So But anyway, you order your primers once you do that. And then this just tells you all the workflow and the equipment, all the details about how you do that. It is very straightforward process. You can see the machine here. They are different smaller size, larger size formats. It got a cartridge where you put the DNTPs, where you put the reaction, where you put your templates, everything. And then all the details of the sample preparation. Okay, we're discussing principle. We're not getting into the detailed technical. I know some of you are interested in the practical. It would be nice, but it's impossible for me to do it in 1 week with all the genotyping techniques. But this gives you a good background, and you can read this internal details, and you can look at it on I believe it's QIAGEN now. It's QIAGEN's database, not Biotage anymore. Okay, you run your sequence. So here is what you get. So let's say you are doing a de novo sequence analysis, or you might be looking at genetic polymorphism. So you look at in specific position. Did I get the expected one, or is it a mixed contamination? Like that's for a question earlier asked as well. So there are sometimes issues that you have a contaminated one, or a purposely spiked sample that we did even with Dr. Ravi, was purposely spiking the vaccine strain with the non-vaccine strain. Let's say position number 5. Some of the strains may have a G, some of the strains may have an A. So you may get a G, you may get an A, but it waits for a sequence. But that position may have 2 different possibilities. It can help you do that. It's a little bit more complicated, but it is possible. Okay. So maybe let's elaborate that question. So now, if you have a contamination, that position has a C and an A. When a T is released, it attaches with those with an A, you get fluorescence, right? But at the same time, if you had a remnant, a leftover G from before, that also can attach at that position because it is double-stranded, TAC is there, it's got the DNTPs, it can attach both. Then you get this, I will show you, so I think I have it, a double bar graph where in the analysis you don't just see it. When you get the output, it will show you that, it will tell you, it will warn you like a warning, like as if it's an error. At a position 5, it looks like you have 2 different bases, or you may have 3 different bases. And by the way, depending on the extent of contamination, as we said at the beginning, the quantitative aspect, it may show you, that graph has a different dimension in terms of looking at. It may show you lots of them have an A, some of them have a G. It's looking at it in a different dimension in terms of how much of the contamination you have. That's the quantitative part. Okay? That's a possibility. In a good way, sometimes when you have a contamination, that could be a useful thing to do. So, but as I said, there is a release is the same, ACGT, ACGT, just it releases turn by turn, and the peak is corresponding with how many bases come sequentially. Okay. Anything fluoresces is what is attached, what is not present. I think that's a key thing. So this is a good example for rifampicin susceptible and rifampicin resistant isolates. So you look at sequences of the specific gene, and then at some position you may have specific changes instead of, you may have TCGG, you may have, you expect TC on this susceptible strain, but you don't see the C on the rifampicin resistant ones. So you may have some mutation at that location. So based on that, you can identify various things. This is similar to the QRDR, like I said, in position number 86 of GIRA for ciprofloxacin resistant Campylobacter. You may have base pair change or deletion mutation that you may skip that. So you will have, the most important thing is you will also always make sure you have the positive controls as well as usually, in fact, negative controls as well. I don't know if we discussed that, by the way, in the amplification. did we discuss negative controls? What negative? Always use controls. Definitely the number one in amplification would be negative controls. What do you use as a negative control? If I am running for meningococcus, specific gene, and I want to make sure the result I'm finding is accurate and not a non-specific band, number one, I base it on the size, yes. I may have a positive control, a known meningococcus from ATCC or from previously known hospital, again amplified, positive, but also a no template negative control is important. No template control, so that you want to make sure that there is no amplification randomly without having a template DNA. So similarly, you'll have a positive and negative controls on your viral reaction. And the genetic polymorphism, its applications could be really wide. One I already said and discussed it quite a bit is on single nucleotide polymorphism, CPRO resistance, rifampicin resistance, other purposes, many other purposes that you may have. But targeted thing you are looking at if there is a change in the base at that location. There are many antibiotic resistance occurred because of a single or a couple of base pair mutations. Rifampicin is one good example, but also ciprofloxacin, some other lincosamides and macrolide resistance as well. So you can look at insertion, you can look at deletion and mutation, you can detect those type of things. Or if you have short tandem repeats, do you remember any tandem repeats that we looked at or discussed? Any that we looked at in the last few days? What? VNTR, variable number tandem repeat analysis. We didn't get into the detail yet, but VNTR, or also called MLVA, multi-locus variable number tandem repeat analysis, is one good example. So there are short tandem repeats. You might be targeting a specific location. So it's good for that study. Or to determine the allelic frequency, getting into a little bit into the quantitative. So various applications that you use pyrosequencing. Epigenetics, I don't know if you do, any of you do, but these are more detailed, not much on epidemiologic side, but this is application, protection assays, islands, DNA methylation or not methylation. There are many functions you use. Yeah, this says you can read it for yourself more in detail, but really you may use it for some other purpose, but not much on molecular epidemiology. Okay, so this is more of on the methylation aspect. So we'll stop here in terms of the basic use of pyrosequencing for synthesis-based sequencing. Okay, but then I will show you the next generation sequences, the mass sequencing using the same technology. There are other technologies, but we can cover that a little bit following this. Okay.